Okay, so hi there. We're now in our next video in Principle of Mathematical Induction. And in this video, I'm going to show more examples of how the first principle, that is the weak version of the Principle of Mathematical Induction works. So we are given this proposition wherein we're going to prove this statement that for any n, which is in the natural numbers, the summation of negative I raised to a certain negative 1 raised to a certain I for all I running from 1 up until it will reach this certain upper limit n is equal to negative 1 raised to n minus 1 all over 2. So that is a claim that this works for all n in n. So we will prove this using, of course, mathematical induction, because the statement says or claims that it is true for any n in the natural numbers. So pretty much we're going to make use of induction here. So let me use a red pen. Let's start with a proof, of course. And for elementary proving, we will state that by induction, or you can use by PMI or by the weak version of induction, whatever suits you, as long as you make it clear that you're going to make use of the mathematical induction. So first, let us say, showing or coming from the theorem of previous theorem, the first principle of mathematical induction, that we have two conditions, and of course we need to start with our letting. So we're gonna let that a certain p of n is a statement that the summation of all minus 1 raised to I, where I runs from 1 to n, is equal to negative 1 raised to n minus 1 all over 2, and that is said to be true. That is for all n and n. Not yet true, but we're going to prove that it's true. Okay, so let p of n be equal to that statement where all these n are natural numbers. Okay, so let's continue. Of course, with our proof, we will start with the base step. So with this base step, what we have here is, in some books they call it the basic step or the basis step. It doesn't really matter what you call it, but we'll call it the base step here. So of course we will set our n be equal to 1. Well, that's the first that is the first natural number there. So that will be our n sub 0 if you're going to stick it from the formula. So we set our n equals 1. And of course, then we have p of 1 is going to be the statement where the summation of negative 1 raised to, of course, our I becomes 1 because that's our upper limit from all I running from 1. So basically, we only have one statement here. Well, negative 1 raised to 1 is clearly negative 1. And that's our left-hand side. We will try to check if that is suiting and that is true for our right-hand side. Negative 1 raised to a certain positive 1 minus 1 over 2. We can actually see from this perspective right here that if we are going to raise this negative 1 by 1, this will leave us out by the value 1. This becomes here negative 1. So basically, if we're going to input negative 1 here, minus 1, this becomes negative 2 for the numerator, and negative 2 divided by 2 is going to give us basically negative 1. So clearly, this works out for the base step that the left-hand side is actually equal to the right-hand side. So we're good with the base step. Okay, so let's delete all those necessary things here. we have just proven that it's true, so we're gonna delete all these annotations. Now let's proceed with our induction step. Of course, we can say that the base step holds as for formality. Next is we want to prove the induction step. So let's start and write the induction step right here. So with the induction step, we will set our n to be equal to some arbitrary value k, where k is in the integers. Clearly, I don't want to set anymore that k is in the integers because n is equal to k, where of course our n is in all natural numbers. So clearly k is also a natural number. So then we have our p of k is going to be equal to the statement summation of -1 raised to k from running from 1 to a certain k. This is equal to our right hand side, which is -1 raised to k minus 1 over 2. So this is our inductive hypothesis. Of course, using induction, we know that we need to prove, or we need to show that if our p of k, if our p of k holds, it should be that p of k plus 1 also holds. So we can just state that suppose p of k is true. Let me write that better. Then we can say that p of k plus 1 is also true. So we can show that that is we have. Okay, so this is where the solvings come in. P of k plus 1 is said to be equal to what's our original statement? Okay, negative, sorry. We start with the left hand side, of course. -1 raised to k plus 1. That's the whole power there, which is equal to I running from 1 to k plus 1. Which we say that this is equal to, sorry, this should not be an equal sign, but colon, equal to -1 raised to k plus 1 minus 1 all over 2. So that's our claim. So we will prove that that will be true. So then we have, okay, cool. We will try to answer the induction step here. So recall that p of k plus 1 can be rewritten as p of k plus a certain -1 raised to k plus 1. Okay, so in this part, I am showing that this is actually true, that p of k plus 1 is simply p of k, that's our inductive hypothesis, plus the next term in this series of sums. So that will be true. So using our inductive hypothesis, this will become, notice that our inductive hypothesis is actually this one. Let me highlight that. This is our inductive hypothesis right here. And we're gonna apply that. So that becomes -1 raised to k minus 1 over 2 plus -1 raised to k plus 1. So first things first, we're gonna make and put them under one under or all over under one denominator. So we're gonna make the 2. So surely how we can do that, we're just gonna put like something like 2 over 2 here. So that just is equal to 1. So just to combine them and put them in the numerator. So we have negative 1 raised to k minus 1 plus 2 times negative 1 raised to k plus 1. Okay, cool. Okay, so in this portion, we will need to recall some laws of exponent. Remember or recall that when, again, I forgot the name of the rule, but it's going to be something like when you have a raised to m and you multiply that by a raised to n, the sum will be, or sorry, the product will be a raised to m plus n. So some examples will be like, say, 2 raised to 3 times 2 squared is going to give you 2 raised to 5. That's 3 plus 2. And you can actually double check that. 2 raised to 3 is 8. We're going to multiply that by 4. That will give you 32. And, that is correct. So we're going to apply that there. Specifically, we're going to apply it in this portion right here with the k plus 1. So let's go. This is equal to negative 1 raised to k minus 1 plus twice the negative 1 raised to k times negative 1 raised to 1. So I guess that's clear applying the rule that I have mentioned right over here. Okay, so applying this one. So we have that. Next line is we need to fix that part there. So we have negative 1 raised to k minus 1 plus, of course, this simply becomes simply just negative 1. So negative 1 times 2, well, is negative 2. Negative 1 times negative 1 raised to k. Okay. Of course, all over 2. Next line is, what we're going to do is we can combine this and this term, right? Because they have the same, say, let's treat negative 1, let's treat this as a variable, so they have the same variable, so they're like terms. What we'll have then is this line. So we have, so of course the coefficient is negative 2 in this part, and this is 1. So that simply becomes negative 1. So how do we write this? Okay, let's write this as it is. 2. Okay. What do we want to end up with? Just like this one. We want to end up with like this one. So how do we do that? Yeah, I think we got it. We will use again the recall that I have here on the left side of the board. So okay, we can apply that in this case here. Notice that it has a negative 1. So okay, let's do that. Let's see. This will become negative 1 plus, because I want to extract the negative 1. So negative 1 times negative 1 raised to k over 2. And then what we have is negative 1 plus, this has a 1, right? So quantity negative 1 raised to k plus 1. Okay, that's what we want. Over 2. By commutative property, this becomes negative 1 raised to k plus 1 minus 1 over 2. And is that it? Yeah, that's it. Okay, so this is equal to, this is just, let me just highlight that this is our left-hand side, which is equal to, what's our right-hand side? Actually, that's basically it. Negative 1 raised to k plus 1 minus 1 over 2. So this is, just to highlight, this is our right hand side. And of course, the left hand side is equal to the right hand side. So therefore we say that then the induction step holds. Okay, cool. So all right, so we're done with the induction step. It took me really quite a lot of lines here, though of course maybe you can find some ways to clear out some of the steps, of course, but this is the first time I answered this, so it's pretty much experimental. Okay, so the induction step and the base step holds, so we can double check that the base step holds, so it's a big check right here. And of course the induction step also holds, saying that of course therefore we can conclude now, therefore by the principle of mathematical induction, if you want to explicitly explain the weak version or the first version, the statement, you can actually just directly write the statement here. What's the statement again? There. So negative 1 raised to I running from 1 to n, is equal to negative 1 raised to, what was that, I, n minus 1, sorry, minus 1 over 2 is true. That is for all n in n. That's the end of proof. Okay, and basically that's it. Let's double check. Maybe I wrote a wrong statement on the conclusion. Let me double check. Is it right? Is it right? Yes, pretty much. So that pretty much shows the solution for this problem, for this proposition that we have. So meaning this proposition is always true. This equality holds for any n in the natural numbers. So thank you very much for watching. I hope you learned something today, and I will see you in the next video. Thank you very much.